anything else because you are tired. Okay? So this is the process. Now let me see how can we okay. Now look at here. Okay? This is how you update your weights. So this delta V is the difference between the weights, okay, at the beginning and after the first iteration. Okay? So we do forward, backward, and then we update the weights. Forward, backward, and we update the weights. Each time we update these weights. Okay? So this is the difference between the old weight and the new one. Okay? This update depends on this function. Okay? Which is, so this is the update of the weight of a generic weight, okay, which belongs to a generic layer L and a generic couple of how can I say, J and K, okay, identify which input unit you have and which neuron you have, okay? So this is one of the many weights you have, okay, in your network. And it is updated, okay, according to what? The delta term, what we have seen before, okay? The activation function for that neuron, okay? And this parameter, which is called learning rate, okay? If you remember, I said you, when you do, so it's a user-defined parameter, okay? And when you do a neural network, you have to set this learning rate. And actually, you can see it as the how much fast you want your network to learn, okay? Because if it's very small, then these changes will be small. If it's high, then these changes will be very high, okay? Okay? So, again, if this is equal to 0, we do not have any update on the weights. Okay? So, then you update all the weights in the network in this way. Okay? And this corresponds to the minimization of the cost function we have seen before. Okay? So the weights are updated, and in this way, okay, looking at these delta terms, this error, then you reduce every time the residual between what you predict and the true class in the output. Okay? Now, we have seen it with one sample. Okay? Of course, it was a question of this morning. I mean, of course, we have many samples. Okay? And as I said, when you train neural networks, you need a lot of samples because, okay, you have to sacrifice some of the samples in the evaluation set or test set. Okay, this is why this morning I said, I mean, to do this kind of approach, you really need information. Okay, so I don't know if you have a data set of metabolomic whatever. I don't know. No one here works with metabolomic data. No. Metabolomic means that you have few samples usually, and thousands of variables. That is not the situation where you can apply this stuff, okay? So, let's say now that we have n samples, Okay, so for each sample we have, of course, a vector holding the variables, okay, we have in the data set. And of course, for each sample we also have the labels of the classes, okay? Then, at the beginning we said, okay, we have now to learn how to update the weights, okay? Not for one single sample, but for all the samples. So, we set to 0 this delta term, okay? And then, do you know what does it mean as a computing language for? It means you repeat this, okay, instruction, okay, for all the samples, okay? So, for all the samples, one at a time, you take that sample, you do forward propagation until the last output layer, okay? So you get the activate the output, okay? Which are the activation function in the last layer, okay? Then, after the forward propagation, then you can calculate, you can go back and calculate all the delta terms, right? For each layer, okay? So for the output layer and for the previous layers. Of course, okay, I mean, this is what I said before. In order to start with this process, okay, we must have some weights at the beginning, and these weights will be random. That means that each time you calculate a neural network, you don't get always exactly the same result. Okay, it's not like LSDA or discriminant analysis. Okay. So, okay, so then we go back, okay, and we compute all these delta terms for all the neurons in all the layers until not the input layer but the first hidden layer, okay? And then we, how can I say, we accumulate all these delta terms, okay? So for each sample, okay, we do the same process and we look, okay, we accumulate all the delta terms which are referred to the weights, okay? So we do it for the first sample and we see which are all these delta errors. And then we do it for the second sample, the third sample, and so on, okay? We do it for all the training samples and then we sum all these delta terms, okay? As we saw before, okay? So we get the delta. For each weight, we have a corresponding delta. And then we have the activation function, and then the learning rate, okay? So we do it for all the samples. Okay. And then, okay, when we have finished, we can update the weights on the basis of these terms, okay? So this is where we have accumulated all these errors. If we divide by n, we have a kind of average error, okay? And we can use that one to make the weight correction, okay? And this is what happens in one iteration, okay? Now we see with a simple example, but did you get how does it work more or less? So we have many samples. We do forward and backward propagation for each sample. We collect all the errors, okay, on the basis of, at the beginning, on the basis of the residual you get in the output layer, and then with the derivatives, okay. We collect all these delta terms for all the samples, then we do an average, and we use that to correct the weights, okay. Let's try to see with a very simple example. So here we have a very stupid neural network because we have 4 layers, 1, 2, 3, 4. We have 2 hidden layers, 1 input layer, and 1 output layer. In the output layer we have just 1 neuron, so it means we are doing a binary classification, okay, 0 or 1. Then we have only 2 features, 2 variables, okay? This is the bias. Here we have just 2 neurons, this is the bias. Here we have just 2 neurons, and this is the bias. And here in the output layer, of course, you don't have the bias because there's one lead. Okay? So, you take one of the samples, okay, and these are the actual values, okay, for that sample for the 2 variables, okay. So now we will do the forward propagation. That means that with the bias also, here I forget also always to put the arrow, okay, from the bias to also this neuron, okay. Anyway, with a linear combination, okay, of these 2 variables, of these 2 values, with the weights we have here, which at the beginning will be random, we get the activation function from this neuron, for this neuron, and for this neuron, okay? And then we do the same and the same. So we will do the forward propagation, okay? So we get the linear combination, then we use the logistic regression function, and we get the 2 activation, okay, for the 2 neurons. This is what we have seen this morning, and what we have also seen before when we were explaining how do we train a network, okay? So then from here again we do the same here, okay? So for example, this is the linear combination of these 2 activation with the bias also, and then from the linear combination with the logistic function we get the activation. The same here, okay? This will be the linear combination of the bias and these 2 activation, okay? These are the weights. We get this linear combination, and then again we get the activation, which is also the output, okay? By means of the usual logistic regression function, okay? And this is the output. So it will be a 1 value, okay, in between 0 and 1, okay? Then we have to do, okay, I don't want to see this. Okay, then we need to do the back propagation, okay? So, you remember we have to get the delta values for each neuron, okay? So here, delta value will be the residual between the actual, the true class, okay, and the output, the predicted one, okay? So again, if these two correspond, then we will not have any update, because this will be equal to 0, and also all the rest will be equal to 0. Okay? And then this is the derivative, okay, of the activation function. So this is how we get this delta term. Then we go back, okay? So if you remember, then we get this from the output layer. We get the delta terms for this second hidden layer, so the previous layer, using the weights here, okay? This delta term and the derivative of the activation functions here, okay? I hope I have put some, let's see. Yeah, okay? So for example, here there is an example, okay? This is the delta term, okay, you have here. So it means that you are going from this layer to this layer, okay? And the delta term here depends on these two errors, okay? D1 free and D2 free, which are the two errors associated to the neurons of the previous layer, okay? Multiplied by the two weights which connect, okay, this neuron to these two neurons. And this is the derivative, okay, of the activation function here. Okay, so this is how we go back. Can you see that? Okay. Again, if this is equal to 0, this will be equal to 0. Okay? And this will be equal to 0. Okay. Or if you want, I mean, if this is very small, this will be very small, this will be very small. Okay? And the update in the weights will be very small. Okay? So if we have a small residual here, then the update is small. Okay? This is another example. This is this delta weight. Sorry, this delta value. Okay? So it's the one associated to the second neuron in the third layer. This depends on what? On the previous layer. Okay, so we have to look at the previous layer, the output layer. So these delta terms depend on the linear combination of this delta, which is the one associated to the output layer, the output neuron, the only one we have. The linear combination of this value and the weight, the only weight that connect these two neurons. Okay, multiplied by the derivative we have here. Okay, so it's exactly as we have seen before. And we go on. Okay, so we repeat this process many times. This is why it takes time. Okay, because we repeat it like hundreds or thousands of times. This is another thing you have to. When you do neural networks, you have to decide how long do you want to train the network. Okay. It can be for a few iterations, or it can be for 100 or thousands of iterations. Even here, depending on how much complex is your data set, okay, and then depending also on the toolboxes you have, because sometimes you have to define how many iterations you want to do. So one iteration, remember, is forward, backward, okay? So sometimes you have to define to do that, 1,000 times, okay? But you can also have a solution where you say to the neural network to stop if this delta terms are very small, for example, okay? Because that means that the network is stable and you are not updating the weights, okay? So there are many solutions that you can adopt. Okay, so of course then, when you get a new sample, for example, a test sample, now, once you have trained the network, the weights are defined, okay? You input your new sample here, the weights are defined, so you just do the forward propagation and you get the output and you stop, okay? And you get the prediction for new samples, okay? So your model, when you do a PLSDA model, for example, what do you need for doing new predictions? If you want to predict a new sample, what do you need? The coefficients, okay? When you do a neural network, what you need are all the weights which constitute the neural network, okay? Because then, then the prediction is very fast, because you have just to apply some linear combination, and the problem is the training. And the most complex part is this one, to decide the architecture, okay, of the network. So these are some of, there is no optimal solution. So there is no an optimal architecture. How many hidden layers? How many neurons? Okay. I don't know. I cannot give you, a general way to decide. So what I usually do is to do this, to test different solutions. Okay. It takes time. These are some of the advices I found in literature, but keep it as really general indications, okay? So, of course, the higher is the number of hidden layers, the complex is your neural network, the higher is the risk of overfitting, okay? So usually one can start with a single hidden layer, which is the minimum, and then you see what happens, okay? Then, how many neurons in each hidden layer? I don't know. Okay, there are very different kind of architecture and structures. As an indication, okay, I found this, but it's not always true. But just to start, one can try to have the same number of neurons in all the hidden layer. Okay, and then remember, okay, if you have here, for example, you have the input, output, and one hidden layer. Okay. This neural network, where you have just one hidden layer, it's also called shallow. Okay, so a shallow neural network is a neural network with just one hidden layer. If you have more than one hidden layer, like here, you have two, or here you have three hidden layers, then you have a deep neural network. Okay, this is the distinction. Okay. I don't know this. Okay. Okay, then I found also this suggestion, but I don't know how much. I mean, he says that the number of how many neurons, okay, I should put as an indication in each hidden layer, okay? And they say that the number of neurons in each hidden layers can be maybe comparable to the number of variables. It depends, because if you have, I mean, a limited data set with 10, 20 variables, it's okay. If you have a spectral data set, I wouldn't do like in the Olmon data set, we have 3,000 or something like that. I wouldn't do a network with 3,000 variables, okay? Yeah. And that's all. Yeah.
How many samples as a rule of
Train,
thumb?
To train a neural network.
Yeah, to say
I
I can
don't
use
know.
a neural network, or let's.
Minimum number.
I would say, let's say that you cannot you cannot classify with standard methods, so you decide to use a neural network. I would say hundreds, at least, I don't know, more than 100, I mean 200, 300, 500, 400. The more samples, the better. Okay, I would never do a neural network with 50 samples, but also because of this, okay? Because I mean, here it takes ages to do all this optimization. Now we can try with MATLAB, but you will see, I mean, it takes some time, okay? So it means that you have to take one evaluation set to test all these solutions and choose the best one. Which means that the evaluation set should be representative of the set of samples, okay? And then you have also the test set that you use to validate, okay? So also this set must be representative. If you have 50 samples, so how would you split the samples in this preset? Let's say you have 50 samples, 2 classes, and you are lucky and the classes are balanced, okay, which is not always the case. How would you split? How many samples in the training, evaluation, and test set? Let's say that you put 50 samples here, 10, and 10. Okay? Is this representative of the full set of samples? I mean, I wouldn't be so comfortable to do this, okay? Because if you are if you take them in a random way, then you are unlucky. Maybe here you have, outliers or whatever. So I feel more comfortable to use neural networks when you have many samples, okay? Even because, I mean, neural networks are also, called black boxes. Because somehow now they have proposed some methods to understand which is the effect of the variables on the classification, for example. Okay, so you can explore the weights, or you can use other methods to understand which are the most important variables to model your data. But what happens inside the neural networks, you don't know, because it's a huge collection of weights which are updated, okay? So with respect to, I don't know, a linear model where you have coefficients that you can interpret, then things get a little bit more complicated for interpretation. Okay? And then it really depends on which kind of data I think you have to model. So if you have, I don't know, spectroscopy data set where PRSDA works, why you have to use these things? But then maybe if you want to do image recognition or whatever, then neural networks can do a lot of things. They have been used a lot for that things. if you want, we can try to use them. Okay?
One more question, maybe something that you already said this morning. Is the learning rate something that you can somehow tune in order to, move from high learning rate to...
Yeah. The error rate, the learning rate influences a lot the network.
So
it's another parameter that you have to take care about. How to choose it? I mean, again, what I usually do is to try different values.
but starting from high value and
Going to low
narrowing down.
values.
Okay.
What do I do? I mean, let me see. Meanwhile, if you want, you can open the classification toolbox, and you can